So, hi Year 12. I'm not being on this video because you don't want to see me, but I thought I'd try and talk you through this PowerPoint a little bit to try and help you. It's quite tricky. If you've not done triple science at GCSE, then you won't know about the chemistry of alcohols, and asking you to research it and do it entirely on your own is a really big ask. I totally appreciate that. So we're going to go over what we mean by primary, secondary, tertiary alcohols, the properties of them, so what are they like, what do they do, oxidizing them, how we do that and what we get when we oxidize them, and then the role of alcohols in forming esters. And obviously it's a real shame we're not in school because that's a lovely practical, makes some lovely pongs. So we use this thing called the R group, which just means the rest of the chain. So if you think about alkanes and alkenes that we've talked about previously at GCSE, you've got all those C's, a chain of C's with H's coming off it. That's what that R is. And instead of having an H at the end of the chain, what you have instead is an OH, an oxygen and a hydrogen. It's called a hydroxyl group, and it gives the name of the chemical anol at the end. So instead of methane, you would have methanol, and then ethanol with 2, propanol with 3, butanol with 4, and then it gets easy to name them after that: pent, hex, hept, oct, non, dec. You just learn to count in ancient Greek, basically. So these are all primary alcohols because the OH group is attached to one carbon. OH group is attached to one carbon that's attached to one other carbon. The OH group is attached to one carbon that's attached to one other carbon. Okay, that's a primary alcohol. This here is a lazy way. It's an abbreviation way of writing primary. We use it quite a lot in organic chemistry, but really you should always write it out as primary. So then, predicting the structure of secondary and tertiary alcohols, you can't do secondary and tertiary alcohols with methanol, ethanol and propanol. You've not got enough carbons. Propanol, actually, yeah, you could, but we're going to do it with C4, so butanol. So the way you get a secondary alcohol is to put the OH in the middle of a chain. So the carbon it's attached to is attached to 2 other carbons. So if I could just go back a slide, with propanol, this is a primary propanol. If that OH group was on that carbon, it would be a secondary propanol. Propan-2-ol, we would call it. This is propan-1-ol, carbon 1, carbon 2, carbon 3. But we could put propan-2-ol, and that would be a secondary alcohol. And that actually affects some of its characteristics, how it reacts and what it produces when it reacts. So primary alcohol, oxygen is attached to one carbon that is attached to one other carbon. Secondary, OH is attached to a carbon that's attached to 2 other carbons. And tertiary, so you need at least 4 carbons in total for this to work, the OH group is attached to a carbon that is attached to 3 other carbons. So you end up with this quite complex branched structure there. Okay, so butan-1-ol, butan-2-ol there. We've started at the other end. You just look where the OH is for naming them, and you give it the lowest number possible. So you could number the chain 1, 2, 3, 4, which would be butan-2-ol. There. If you numbered it this way, butan 1, 2, 3-ol, that would be wrong because you always try and have the lowest number possible. And then suddenly the name looks horrible, and I couldn't find a displayed structure without making my own, and I was lazy and I just pinched one off Google. But wherever the lines meet, or wherever there's a corner, there's a carbon there. So there's a carbon there, one there, one there, one there. And whichever way you look at it, 1, 2, 3, or 1, 2, 3, it's a 3 carbon chain. Stop pressing stuff. So it's prop, meth, eth, prop, 3 carbons. So it's propan-2-ol. If you ignore the top part there for a sec, 3 carbon chain, propan-2-ol. But we've also got the CH3 group, a methyl group, which is also on carbon number 2. So 2-methyl, propan-2-ol. So the rules for naming them is you look at the longest chain first. If there's more than one OH group, then you use di and tri. So a diol if there's 2 OH groups, or triol if there's 3. And you number the carbons to try and get the lowest possible numbers. And then if there's any other side groups, you need to add those on at the beginning. So you kind of name them in reverse. That's how I think about it. So looking at that one there, so wherever there's a corner, a bend, you've got a carbon. So you've got 1, 2, 3 carbons, meth, eth, prop. So it's propane. Name the longest chain. Is there more than one OH group? Yeah, there is. There's 2. So it's going to be a diol. Those diols are on carbon number 1 attached there and carbon number 3. So it's propane 1,3 diol. But there's also a methyl group attached to carbon number 2. So 2-methyl propane 1,3 diol. Sounds horrible, but the systematic way of naming the organic chemicals is actually really logical once you start a bit of practice. And the thing about this, can't remind you often enough, there's no exam on this, it's just for the assignment. So, drawing out different isomers. An isomer is where you have 2 or more compounds with the same formula, but the atoms are arranged differently. It's a bit like having some Lego blocks where you could make a model of a house, or you could take it to bits and make a model of a boat. Different models. So the same thing. 4 carbons, 1 O, 1 O, 1 H. And you always want to have the OH because we're looking at alcohol, so you keep the O and the H together, and you could do it like that. So meth, eth, prop, bute, butan 1 ol, butan 2 ol. Longest chain here is 3, whichever way you look at it. So the chain is meth, eth, prop, propane, propanol, 2-methyl propan 1 ol. And then this one is the same as we had before. Prop, propan 2 ol, 2-methyl propan 2 ol. Primary alcohol, secondary alcohol. Primary alcohol, because this carbon is only attached to one other carbon, and this one is attached to 3, so it's a tertiary alcohol. So, properties of the alcohols. So how volatile something means, it's one of those words we use differently in chemistry to everyday English. How volatile something means, how easy is it to evaporate. So methanol is a liquid. Methane is a gas. The only difference between the two is the presence of an oxygen atom. Methane, CH4. Methanol, CH3 with an OH on it. Why does it make a difference? Well, alkanes are non-polar, very weak forces holding the covalently bonded chain together. And methane is a small molecule, CH4. It's the smallest organic molecule there is. Really weak intermolecular forces. You've done about those with Mr. O'Connell. Whereas alcohols have the OH, and that's polar. So they've got hydrogen bonding, and that's a much, much stronger intermolecular force. It's the strongest intermolecular force there is. So you require a lot more energy to separate the molecules. So they're held together more strongly as a liquid. All the molecules are touching, but arranged randomly like you learnt back in year 7, compared to methane, which is a gas. So it's less likely to evaporate than methane. However, if you go, let me go back a sec. If you go along the chain, so methanol, ethanol, propanol, butanol, as the chain gets longer, there's more intermolecular forces. It's a bit like having the amount of Velcro together. The longer stretch of Velcro you have, the more force is taken to separate it. So octanol, 8 carbon chain, the molecule's bigger, so it will have a higher boiling point, will take more energy to separate it. It will be less volatile. If you spill ethanol on a surface, on yourself, it feels cold because it evaporates so quickly. Something like octanol would feel oily and would sit there a lot longer. It doesn't evaporate. So the longer the chain, the less volatile it is. Solubility, similar kind of thing here. We would do this as a practical in the lesson. Methanol, short chain, 1 carbon. Pentanol, slightly longer chain, 5 carbons. What you find when you mix them with water is the presence of the OH group in the methanol helps it to mix with the water. It's soluble. And the same for ethanol. I mean, otherwise alcoholic drinks wouldn't work. The alcohol in alcoholic drinks mixes with the water in the rest of the drink. Once you get to a few more carbons, 5 carbons there in pentanol, That doesn't happen anymore. There's too much carbon. There's too much of the non-polar part that can't mix with the water. So it's insoluble. You get two layers. You get like an oily layer and a watery layer. Wouldn't look so pleasant if you tried to drink that. Don't ever try and drink pentanol. It's very poisonous. So as alkyl chain length increases, the OH group has less influence over that CH chain, so they're less soluble. We'd also do this as a practical. The shorter the chain, sorry, getting wobbly hands now. Shorter the chain, the cleaner the flame. You get a nice blue flame when you burn methanol. By the time you get to ethanol, propanol, they're starting to get a bit yellow, a bit sooty. And that's just because you need more oxygen to oxidize all those extra carbons into carbon dioxide. So you end up with more incomplete combustion, which is, a problem environmentally, things like that. Okay. Not far off there, promise. Oxidation of alcohols then. You add an oxidizing agent, and we use something called acidified potassium dichromate. It's a lovely bright orange and it goes really dingy green in this reaction. Primary alcohols, where that OH group is right on the end of the chain, if we oxidize them, to start with, they will become an aldehyde, which has this functional group here. Now, because if you've made your list, you'll know about this. Carbon to double bond oxygen is called a carboxyl group and has its very special set of properties. And then this also just to a H. That's called partial oxidation. If you carry on oxidizing it, the aldehyde will then become a carboxylic acid. You've still got the carbon double bond oxygen, you've got that carbonyl group, but you've also got a hydroxyl group, and this whole thing becomes a carboxyl group. Total oxidation. Carboxylic acid. The most common one we talk about is the one with 2 carbons, ethanoic acid. Some used to be called acetic acid, more commonly known as vinegar. So that's why if you leave a bottle of wine or beer out open for too long, open to the atmosphere, over time it will oxidize and it will become vinegar. That's why it tastes horrible if you leave it out for too long. So drawing out, we don't need to do that. You can do that. Now the way we do it is to use a set of equipment that's called distillation. And that does your partial oxidation. So you heat up your alcohol, you heat up the acidified potassium dichromate. The reaction occurs very hot, so it vaporizes, the gases rise, come down through this, which is a Liebig condenser. You can just call it a condenser. You should have seen that before. It has a jacket around it. You attach it to the taps. They sort of don't include that on the diagrams because it starts looking too complicated, but constant flow of cold water in there, up, surrounding these gases and out the other side. So it's constantly cold, and the coolest part down here to make sure that all the vapours condense again. So evaporation followed by condensation is called distillation. And your product is collected at the end. So methanol makes methanal, propanol, propanal, decanol, decanal. If you take that condenser, that's partial oxidation of primary alcohol. If you take that condenser and you put it vertical on top of your reaction vessel, what happens is that when everything is boiling, your reaction mixture, your aldehyde is in there and it evaporates just as before, hits the condenser, condenses back to a liquid and drops back in. Instead of being collected off separately, it drops back in. And that means it's heated more and it will continue to react. So this is called reflux. If you've heard, you might have parents or grandparents who've had acid reflux, is when acid in your stomach rises up a little bit too far back up the digestive tract, and it's really uncomfortable. It's this idea of something going up and down is reflux. So heat the mixture and it goes up, condenses and falls back down, continues to react. So the reaction goes completely through the phases of primary alcohol to aldehyde and finally to carboxylic acid. So when you're oxidizing a primary alcohol, there's 2 possible options depending on which equipment you use. That for the partial oxidation to get your aldehyde. Condenser on an angle like that. That's distillation. Go back up. Distillation, or reflux to get your total oxidation, which is where you get a carboxylic acid. And the endings, so have to be careful how we say this. Partial oxidation makes an aldehyde. The ending is anal, methanal, propanal. Whereas if we're making the carboxylic acid, the ending is anoic acid. So methanoic acid, 1 carbon, propanoic acid for 3 carbons, and so on. See what I mean? Hopefully see what I mean about the naming being fairly logical. You just have to learn to count in another language, basically. It's no different to undern, or 1, 2, 3, meth, eth, prop. So that's just a sort of a summary slide there to show the different methods. Distillation, reflux. Angle, vertical, partial oxidation, total oxidation, makes an aldehyde, makes a carboxylic acid. Okay, done that bit. Right, a secondary alcohol here, a primary alcohol there, the secondary alcohol here, okay, makes something called a ketone, okay. So in the primary alcohol, what happens when it's oxidized is that this 2 H's are removed and this H stays there and you get a double bond here. On a secondary alcohol, when these 2 H's are removed by the oxidizing agent, there's no H here or directly linked to this carbon to be removed. So when you have a double bond there, what happens is it's just a double bond basically in the middle of a chain. And that's called a ketone. Should have a diagram there. So carbon, carbon, carbon. Acetone is the old-fashioned name. You might know acetone from things like nail varnish removers or paint strippers, things like that. But it's 3 carbons, so it's propanone. 3 carbons and a double bond to an oxygen. Okay? And it doesn't matter what technique you use, either distillation on an angle, reflux, vertical, doesn't matter. There's no other option. You only have one possible product with secondary alcohols. It will always oxidize to a ketone. This symbol here, again, is reflecting that we're using acidified potassium dichromate. Just saves you having to write all of that out every time. It's your oxidizing agent. So primary alcohols, just go back a sec. There. Primary alcohols, partial oxidation produces an aldehyde. Total oxidation produces a carboxylic acid. Secondary alcohols will produce a ketone. That's it. Tertiary alcohols, no, there's nothing. There's no hydrogen that can be removed from this carbon. Okay, it can take that H there, like it's done here, and like it's done here, but it's always taken that H as well. That H as well. It can't take a H from those carbons. They won't be prepared to give it up. So that's easy to remember. You can't oxidize a tertiary alcohol. You don't get a product. Okay, and then we'll do aldehydes and carboxylic acids as a separate sort of chapter of our functional group handbook that we're working on later on. So the very last thing, I'm going to try and keep this video, well, 20 minutes is looking slim, but not much longer, I promise. What happens if you get that carboxylic acid, like vinegar, and you react it with an alcohol? It makes a new chemical called an ester. A lot of functional groups we've talked about here. We've talked about alcohols, aldehydes, carboxylic acids, ketones, esters. If you didn't do triple science, that's 5 new functional groups all in one session. I appreciate that's a heck of a lot. So the reaction we would do, quite simply, is in the lab, you'd get a little bit of alcohol in the bottom of a test tube, add a little bit of carboxylic acid, add a drop of very concentrated sulfuric acid, it's just a catalyst, and you'd warm it up a bit in a nice warm water bath. You could then neutralise it, just to make sure that's what the should say here, sodium bicarbonate. You neutralise it by pouring it into that, and the ester will float on the top, and you get a nice fruity smell. And there's a load of different ones. There we go. So, depending on what ester you've made, it might smell like a different fruit. And when we do this, people they look at me like I've gone mad, because basically everything smells of chemicals. But if you can use your imagination a little bit, some of them, this one certainly works. I definitely get orange smelling from that one. Ethyl ethanoate, which is not on here, is another one that smells like pears, or better still, pear drop sweets. Esters are used a lot in fragrances and also flavourings. I mean, they occur naturally. You know, ethyl butanoate is naturally in pineapples. So, the first thing is how we name them. And the one that you needed to know if you did triple science was that ethanol and ethanoic acid made ethyl ethanoate, but you didn't have to really explain it. So it's easier to see if you pick a different alcohol and a different acid. Methanol loses its alcohol part and just becomes methyl, just a CH3. And propanoic acid, methyl propanoate. So the first part of the name comes from the alcohol, the second part of the name comes from the acid. The same is true here, but you can't really tell because they're both eth, so it's a bit confusing. First part of the name comes from the alcohol, second part comes from the carboxylic acid. So with that information, I could give you any alcohol and any carboxylic acid, and you could name the ester that is formed when they react. The next thing is drawing them. So we've just said what happens. And the alcohol with its OH loses its OH. Is the easiest way to think about it. If you were to go on and study chemistry at university, they might argue that this way isn't totally accurate, but it's the easiest way to think about it. So there we've got our ethyl, our 2 carbons and 5 hydrogens, and that bond, ready to bond to something else. The carboxylic acid loses its H. That's all. Just that H. It's an acid. Acids react by losing their H. Okay. So then you've got OH and a H, 2 H's and an O, H2O. So that makes water. And you've got these carbons here that want to bond to something, and this oxygen here that wants to bond to something. So all that happens is that this carbon comes round here and bonds onto that oxygen. There will be videos of this on YouTube if you need. Okay, so we lose the OH from there, lose the H from the acid, and they join together. And there you can see you've got what was left of your carboxylic acid and your alcohol. It's ethyl ethanoate. And it's the same. It wouldn't matter. You could have the most complicated looking alcohol and carboxylic acid, lose the OH, lose the H, join them together. That's all that happens. So, ethyl propanoate. There you've got your 3 carbons for propanoic acid, and butyl ethanoate. 4 carbons were in your butanol originally, and ethanoic acid. We tend to draw them convention, Google clearly, because that's where I've got these from, shows them this way round with the carboxylic acid bit up here, the double bond and the single bond oxygen that way. It's just convention. It doesn't matter. Okay. So, like I said, you can have one that looks absolutely awful. So salicylic acid here is an acid, but it's also an alcohol. And acetic acid, lose the OH, lose the H. Okay. This isn't an alcohol group because it's joined to a carbon with a double bond oxygen. So that has to be a carboxylic acid. Okay, so there's the alcohol group. Lost the OH, lost the H, joined on. And that's actually aspirin. Okay, so esters are pretty important, worth knowing about. So same again there. Lose the OH, lose the H. Okay, that one. We actually make that in the lesson as well because that smells quite recognisable. Oil of wintergreen is a chemical that you get in things like deep heat. It's that quite medicinal type smell. And that's it. I've made it. Just about 25 minutes. I hope that helps. I know I've waffled on a lot, but I think talking through the presentation has hopefully made things a little bit clearer. We will go over this in the lessons when we get back. I don't know what's happening with lessons before the end of this term. We've sort of got a vague plan for year 10. I've not really had anything confirmed for year 12. It's a bit tricky because both Mr. Gunter and Mr. Russell are involved in teaching A-level biology and physics respectively. And both myself and Mrs. Kendall, who's been teaching the year 13 stuff, there I am, is... we both have 4 children at home, so I'm not sure what's happening. I'm not sure if I'm going to see you before September. But anyway, all the best. Take care. I'll see if I can upload this somehow now. And just look after yourselves and be good.